Hello everybody. Today we're going to be talking about what makes a magnet a magnet. So you're going to want to make sure that you have out your Inside a Magnet note sheet while I'm talking about this. One easy way to have it open kind of side by side, if you didn't know this already, is to just minimize your screen and then pull your notes over to the side. And then you can kind of adjust them and fiddle with them and make them the size that you want them to be, so that you can then kind of type into them. Right, so that's an option if you want to be able to have them both open next to each other. Alright, so I'm going to get started now. Alright, so I'm going to be using these words. They're words that you don't necessarily have to write down right now. They'll be vocab words you'll use later. And I'll briefly mention kind of what an atom is, a nucleus, a proton, a neutron, an electron. I'll show you a quick diagram. Just a quick reminder, you've probably heard of atoms before. They're the smallest particle of an element that retains all the properties of that element. Just means it's the smallest building block. It's what everything is made up of. Alright, these are the vocab words that you want to make sure you write down on this sheet. Magnetic domain, ferromagnetic material, temporary magnet, and permanent magnet. These are important words for this section. Go ahead and pause to write those down. Alright, so next up we want to make sure we get a good picture of an atom that's labeled. You can do this two ways. You can either do this in the drawing tool on Google Docs, or if you prefer to hand draw it and label it, you can take a picture and add it to this document if you want. So what we want to make sure that we include on this atom, these are the pieces. We need a nucleus, right? That's the center of the atom. And inside the nucleus you'll find neutrons, these are these things in blue, and protons, those are the things in red that have the pluses. The reason that they have the pluses is that we say they have a positive charge. So when we talk about protons, and you'll learn more about them a little bit in chemistry, but they're positively charged. Neutrons, we call them neutrons because they're neutral. They have no charge. Now, they make up most of the actual bulk mass of the atom. Outside, zipping around, there can be any number of electrons. They're very, very tiny compared to the neutron and proton. And they have a negative charge. That's why you'll see them with a negative sign next to them. Alright, so these are the important parts of an atom, and we'll figure out in a minute how this relates to magnetism, but this is important. Alright, so make sure you have all the pieces and they're all labeled properly. Alright, how a magnetic field is produced in an atom. There's something called electron spin. Right? These electrons, like I said, they're spinning around the nucleus, and as they're doing this, they produce a magnetic field that makes them act kind of like a magnet. That gives them their own little mini magnetic field. Right? So here's our little electron zipping around its nucleus, and it's created its own little magnet, a South Pole and a North Pole. Right? Magnets and electrons, in order to actually be a magnet, there are some things that have to happen. So not every atom, just because it has electrons, becomes a magnet. What ends up happening is most atoms have paired electrons. So as they're zipping around, right, you've got two electrons, they're right next to each other, they tend to be paired off. And these electrons, they spin in opposite directions. So this one might be spinning this way, this little electron is spinning in this direction. And what that ends up doing is creating opposite poles that cancel each other out. Right? They each have a magnetic field that they've created. Right? Each electron is its own little magnet, but its own little magnet that has now canceled out the other one. So when you have two electrons paired off in an atom, they cancel out, you end up with a very weak magnetic property. And that's most atoms tend to have this very weak magnetic property. They tend to have paired off electrons. Little to no magnetic field. In order to get a strong magnetic property, right, you have to have atoms that have some electrons that are not paired. So here's an example of one. You can see it does have paired electrons that are zipping around together, but then it's got these kind of loner electrons that are all by themselves, and their magnetic fields are not canceled out. Right, so they end up having a strong magnetic property. Right, so this single atom would have a magnetic charge because of its kind of lone rebel electrons all by themselves, very lonely. Alright, so quick recap. Materials contain atoms. Atoms contain electrons. Electrons spin, creating magnetic fields. Most atoms have paired electrons with magnetic fields that cancel each other out, hence their very weak magnetic properties. Alright, so let's talk a little bit about magnetic domains. For most materials, the magnetic fields of their atoms cancel each other out, like we said, but the magnetic fields of these materials aren't necessarily detectable because of this. Right? So when we talk about a domain, we're usually talking about a number of atoms all grouped together and what direction they're facing in. So in order for it to be a domain, they've got to be facing the magnetic domain. They have to be all facing, lined up perfectly, facing the same direction, or almost all facing the same direction. There can be some that are a little rogue. If they're all scattered all over the place, like they are in most materials don't have atoms all perfectly aligned, it's not going to be magnetic, and it's not a magnetic domain. Okay. So magnetic domain definition, for some materials the magnetic fields of groups of atoms point in the same direction. This group of atoms is called the magnetic domain. The entire domain acts like a bar magnet. So certain materials can become aligned, right, and all of their atoms all line up facing the same direction. That becomes a magnetic domain. Right. So just to recap, magnetic domains. A magnet, when all or most magnetic domains inside a material line up, so those groupings of atoms all line up in the same general direction, that's a magnet. When the magnetic domains inside the material don't line up, they end up canceling each other out, right, like the domains in this material, and that is not a magnet. Right? Magnetic materials, the domains do line up. Right? Non-magnetic materials, they point in all sorts of different directions. Okay, so here's just another diagram. The arrows represent the direction of the magnetic field in a magnetic domain. So you can see all these little atoms, they're all facing in different directions. Their magnetic fields are all just canceling each other out. Okay. When the magnetic domains point in the same general direction, the material becomes magnetized. So see how they're basically all pointing to the left here? That's a magnetized material. It's actually iron specifically. Right? So this leads us to one of our vocab words, ferromagnetic materials. Ferro comes from the Latin word meaning ferrum, which is just iron. Right? Ferromagnetic materials are not naturally magnets, but can become magnetic. So they're materials that can be, with a strong magnet, their domains can be all switched to face the same direction. They can become kind of a temporary magnet. And iron is an example of that. You can magnetize iron and make it temporarily its own little magnet. Alright, so a material that's strongly attracted to magnetic fields and maintains magnetic properties after being in a magnetic field, such as iron. Alright, some other examples might include nickel, cobalt. There's some rarer ones like neodymium. Also alloys, which are just mixtures of metals that contain things like iron and nickel and cobalt. Aluminum's an example. Steel. One thing that's commonly used in magnets is ferrite. You can actually make something a magnet if you want. You can place a ferromagnetic material that is not already magnetized in a strong magnetic field. So you can actually place something like a paperclip in a magnetic field and cause it to be temporarily magnetized. you can rub a magnet's pole over the material, and this can cause the domains to align inside the material. So if I were to take, let's say, a paper clip, like this one, and rub, we'll see if this actually works, it's a little tricky. If I were to rub a strong magnet onto it, right, I could potentially magnetize briefly the paper clip and cause it to hold another paper clip. Right, so this paper clip, it's not going to maintain this magnetization. After a little while, this paper clip's going to drop. I'm not going to be able to pick it up again. But you can see it's retained some of the magnetization. When I rubbed the north pole of this magnet onto the paper clip, oh, there it goes, it caused all of the little atoms and domains inside the paper clip to align, and it caused it to become, temporarily anyway, magnetized. And yeah, it very quickly goes away. But you can try that. If you have a magnet and a paper clip, you can give it a try. You might be able to get it to work. Alright, you can also destroy magnets along with creating them. There's two ways to do that. You can hit the magnet with a large force. So when all of you are out there dropping your magnets, you're actually weakening them a little bit. You're shaking them out of alignment, all of their domains. And you can actually destroy it. The other way is to heat the magnet. Right? If you heat it to a certain temperature, that can also destroy all the domains that are facing and aligned. That can get them all out of whack, and it's no longer a magnetized material. Alright, so in both cases, the magnetic domains become unaligned. The material loses its magnetic properties. And here's just an example. Right? You have a strong magnetic field, you apply heat, or maybe you shake it up, and you end up with a weaker magnetic field. Alright, most of the magnetic domains of a magnet point in the same direction. When a magnet is broken, the magnetic domains still point in the same direction. So each piece has both a north and a south pole. So this is if I were to take this magnet and just snap it in half, right? They would still all be facing in the same direction. It would just become two separate little magnets, right? So what would end up happening if I broke the south and the north off, this south side would rebuild a north side on this end, right? And the north side would have a new south side up here on this end. So just snapping a magnet in half only creates more tiny little magnets, right? The domains don't actually get messed up, so it still remains magnetized, just breaking it in half. Okay, this is just another example. And this actually would be kind of a good diagram to have, so you know what happens when you snap a magnet in half. And also, just you can see the magnetic field really well in this diagram too. Alright, that's it for Inside a Magnet. Make sure you've completed your worksheet, and have a great day.